All right, good morning, everyone. Let's start. Okay, so in the previous class, I was talking about channel coding, and in particular, we looked at discrete memoryless channels. So recall that we model the channel as a random process. Essentially, the channel takes n symbols as input. It takes xn as input and outputs a sequence of n symbols, and yn, the output of the channel, is random, conditioned on xn, and the relationship between xn and yn is specified by the channel transition probabilities or the channel law pyn given xn. And a discrete memoryless channel is one where the pyn given xn is basically the product of all of the i's p of yi given xi, right? So each symbol xi gets transformed into a random variable yi, and all of them are, and this process is independent and identically distributed. And we saw some examples of discrete memoryless channels, the binary symmetric channel, where each bit gets flipped with a certain probability, the binary erasure channel, where the input is a bit, and the bit can get erased or remain as it is with a certain probability. Right? And then we also saw additive wide Gaussian noise channels, wherein each symbol is corrupted by adding a Gaussian random variable zi. So yi equal to xi plus zi, where zi is Gaussian with mean 0 and variance sigma square. And in particular, in this case, we saw that either we can impose a certain constraint on the input alphabet. So xi can come from some particular constellation. So this is the constellation constrained AWGN channel. Or we can say that there's no constraint on the constellation, but there is instead a power constraint. And the power constraint is that 1 over n times the summation of all of the i's xi square, this should be less than or equal to p. So this is an L2 norm constraint on the input vector, or also this is also called the power constraint on the input. All right. So these were all discrete memoryless channels. Now the AWGN channel, as I mentioned, can be generalized to wireless fading channels, where each yi is hi times xi plus zi, where in addition to the zi's being Gaussian, the hi's are also IID according to whatever distribution you want. Right? But then there are more general fading models, such as the frequency selective fading channel, where each yi can depend not only on the current input xi, but also potentially on the previous inputs. So it depends on yi can depend on xi minus 1, xi minus 2, and so on. But this does not form a discrete memoryless channel. So this is a channel which has memory. And the discussion in this particular course will only focus on discrete memoryless channels. So we won't really focus on channels of this particular form. All right. So are there any questions from the previous class? Any questions? Okay, so we'll study discrete memoryless channels in a little bit of detail. So what is the goal? So right now we have defined what the channel is, but then the problem is, how do we communicate across this channel? Right? So the channel is given to us. We have absolutely no control over it. Right? It is completely specified by this channel transition probabilities or the channel law. So this is known as a system designer. We know how the channel behaves or the statistical behavior of the channel, But our goal is to somehow transform uh, the data that we have into some particular form, so that ultimately we are able to recover the original message or the original data. Right? So the goal is to construct these algorithms or these blocks, the channel encoder and the channel decoder. So the channel encoder is going to be some function which takes k bits as input, right? So these are going to be our information or data or message bits. Right, so we have k information bits or k message bits, and these are encoded to give an n length vector. So the n length vector obviously has to come from the input alphabet to the channel, right? So this is a sequence of length n. This is sometimes called the code word. Right? So the k message bits are converted to n code word symbols, and these are sent through the channel, right, one after the other. Now, corresponding to each input symbol or each code word symbol, there is the receiver gets yn, which is the received vector, right? And then we have a decoder block, a channel decoder block, which takes the received vector as input and outputs the estimate of the message bits. So this is the decoded message or the estimate. Right? So our goal is to ensure that, well, the decoded message should be equal to the actual transmitted message. Right? So we want to ensure that mk hat is equal to mk at least almost all the time, if not all the time. We want to make sure that these two are equal most of the time. Right? Or the probability of error that mk hat is not equal to mk should be as small as possible. But in addition, we want to make sure that we can transmit as many information bits as possible through the channel in every channel use. Right? So our measure of performance of any particular coding scheme. So a coding scheme consists of an encoder and a decoder. So this is the coding scheme. So the coding scheme consists of an encoder which takes k information bits as input and outputs a code word of length n. And in addition, there is an associated decoder which takes the received vector of length n as input and outputs a sequence of k bits. Right? So the performance of the coding scheme is characterized by these two metrics: the rate, which is k over n, which is basically the number of information bits which are sent per channel use, remember that the term n is called the number of channel uses, or also sometimes called the block length. So k over n is the number of information bits sent per channel use. So the larger k is for a given n, the better, because you're transmitting more information bits per second or per channel use. Right? So this is the rate, and we want to ensure that the rate is as large as possible. The second parameter that we're interested in is the probability of error. So this is the probability that the decoder makes an error. Right? So we'll measure it using this, what is called the average probability of error. The average probability of error is basically the probability that mk hat is not equal to mk, assuming that each message occurs with equal probability. Remember that the message is a sequence of k bits. So we'll assume that each bit is IID Bernoulli half, right? So basically IID Bernoulli half. So it's a sequence of k uniform bits. And the reason why we make this assumption is because now if you go back to the original block diagram, the input to the channel encoder is basically the output of the compressor. Right, so it's from the compressor block, you go to the channel encoder block, and if you use a good compressor, then the output of the compressor is going to be a sequence of k bits, and these k bits are going to be close to uniform. Okay. So our goal is to design these coding schemes, that is encoders and decoders, such that the rate is as large as possible and the probability of error is as small as possible. All right, any questions? Okay, so let's think about what the encoder would look like. All right, so assuming that we're not doing using any sort of fancy algorithm, one way to think about the encoder is as a lookup table. All right, so it's basically a function which takes the k-bit message as input and outputs a sequence of length n. So one way to implement the encoder, it's not an efficient way of implementing the encoder, but a very generic way of implementing an encoder is the following, where for each, so it's basically going to be a lookup table. For each sequence of k bits, you have a corresponding code word, right, of length n, and you store this as a big table. So when you get a particular message, suppose that you have to transmit some particular message, maybe this particular message, then you go to the lookup table, you read that particular row of the lookup table, and then find out what the corresponding code word is and transmit this across the channel, right? So basically what you have to do to design the encoder, all you have to do is somehow fill up this lookup table, right? So for every message, you need a particular code word, which is going to be some sequence of n symbols, right? So, and each of these is going to come from input alphabet raised to the n. Okay. So the goal is to somehow design this lookup table. So encoder design basically corresponds to designing this lookup table over here. So for example, if you're using BPSK, then the lookup table could look something like this. So the two symbols in every channel use, you can either send plus square root of p or minus square root of p, and then you sort of design this table. So for each sequence over here, each k-bit sequence over here, you have an n symbol sequence over here. Okay, and the goal is to somehow recover back the message given the received sequence. Now, suppose that I'm transmitting these code words through, let's say, an AWGN channel. Then what happens? I'm going to transmit a sequence of n symbols, which is plus square root of p minus square root of p. But then what I receive is going to be a sequence of n real numbers, not necessarily plus square root of p and minus square root of p. If the noise variance is small, then it's going to be close to these, right? Yes.
Sir, what is this under root p symbolizes?
So p is some parameter, right? So for example, maybe this is the encoding. So as an example, consider suppose I want to send 4 bits. These are my message bits. Now corresponding to this, I'm going to have, let us say, the following code word, plus square root of p minus square root p plus square root p minus square root p plus square root p. Okay, so my sequence of k bits, this is my mk, is going to get mapped to some particular vector. Maybe my power constraint p is let's say 4. So basically 0, 0, 0, 0. is going to get mapped to 2, minus 2, 2, minus 2, 2. So this is going to be my xn, and this is sent through the channel. So in channel use number 1, I'm going to send, say, plus 2. In the second channel use, I'm going to send minus 2. In the third channel use, I will send plus 2. The third channel use, so fourth channel use, I will send minus 2. And fifth channel use, I'll send plus 2. Right? So if you look at x of I versus I, where I are the channel uses. So basically what you would send would be the following. So it is plus 2, minus 2, plus 2, minus 2, and plus 2. So this would be sort of the input signal to the channel. Right? So this is 1, 2, 3, 4, 5. So this is the input signal to the channel. You're using 5 channel uses. Now, at the receiver, maybe this gets corrupted. Maybe this is sent through an AWGN channel. So the received signal, let's say y of t. Now again, it's a discrete time signal. So each x of I is going to be corrupted by with some AWGN. So maybe the received sequence is now going to be look something like this.
Sir, you like 2 minus 2, 2 minus 2. There's a first channel, second channel, third channel. Like
So it is a third channel use. So think of this as different instances of time. It's a discrete time signal, right? So in the first time instant you send this, second time instant you send this, third time instant you send this, and so on.
right.
All right. And then what you receive in the first time instant is going to be some corrupted version of this. Second time instant, it is going to be some corrupted version of this. So maybe what you receive, so the yn could perhaps look something like 1.2 minus 0.7, 0.2, maybe minus 2.6. And then the third, you get maybe something like 1.3. So this could be the received vector. In time instant 1, you get this. The second time instant, you get this. Third time instant, you get this, and so on. This is one sort of made up example for the received sequence. Okay. So given this received sequence, you somehow need to get back the original message sequence. Yes.
So this I didn't get it. What is x of I and y of t that you have written?
So basically these are different representations of the same thing, right? The input is xn, right? So it's a vector of length n, but each component is so you can view this vector of length n as basically, so this is going to be a discrete time finite length sequence. Right, where the first component is sent in the first time instant, the second component is sent in the second time instant, and so on. Right? So it's another way to represent a discrete time signal of finite length. Right? It's just a vector. Right? So
so that whatever 0, 0, 0, 0, 0 example that you've taken,
correct.
so that is the input to the channel encoder.
No. Yeah, correct. So this is the input. So this is the input to the channel encoder, and this is the output of the channel encoder.
And this y of t is the output of the channel.
Is the output of the channel.
Okay. So that is why it is like some things are added or subtracted. It's
Exactly.
correct.
Exactly. So it's some corruption of x of t.
Okay.
So each y of t is an independent corruption of x of t.
Sir, in the
Yes.
channel encoder, so compared to the input of the channel encoder, channel encoder output length is greater.
It's greater. It could be greater. Yes.
And will it be? I mean, would it be just binary? Because here you're giving some other value like two minus
So
two.
I'm allowing any general encoder, right? So it need not be the case. So each y of t. So the output of the channel. Okay. So you have the input to encoder, and then this is converted by the channel encoder to the output of encoder, which is basically the input to the channel, and then from this you get the output of the channel or the input to the decoder, and then the output of decoder. So I'm assuming that the input to the encoder is mk, the input to the channel is xn, the output is yn, and the output of the decoder is nk hat. Right? So let's look at this particular relation. Let's first look at this particular relationship. Now, so I can view this as x of 1, comma x of 2 up to x of n. Right? And similarly, I have y of 1 through y of n. So each y of t depends only on x of t. So given x of t, y of t is independent of everything else, and that is because this is a discrete memoryless channel. So for example, in an AWGN channel, each y of t is obtained by adding Gaussian noise to x of t. Correct? But on the other hand, I'm imposing no such restriction for the channel coding scheme. Right? So the encoder could potentially, so each x of t does not necessarily depend only on m of t. And that is why I'm allowing this k and n to be different. So this could be any complicated function of m of t. So one sort of simple, not complicated system would be, again, you have a sequence of bits, and then you convert this directly to BPSK. So maybe plus root p, convert a 0 to a plus root p, a 0 to plus root p, a 1 to minus square root of p. Right? So this is one potential channel encoder. But then I'm allowing you to construct more complicated channel encoders as well, where k is not equal to n, and this mapping from m to x, it need not be component wise. Right? So this the first component could potentially depend on all the bits, message bits. All right, and in fact, it turns out that if you a good channel encoder is one where where each symbol depends on all of them or most of the message bits. So such simple component-wise mappings are not good. Is that clear? Any questions?
So this is like that example where you said in a mail we don't take letter by letter and instead of word, something like that.
Sure. So a better analogy is sort of something like, so for example, okay. So one, we'll explore a couple of simple schemes later on, but yeah, so that's perhaps not the right analogy. So here is one potential scheme. Okay, so let us assume that both mk and xn are binary. binary. Okay, or maybe xn is not necessarily binary, maybe nk is binary. Right. So one way of getting xn, one sort of way to think about it is that maybe xn is obtained by a linear transformation of mk. Right. So xn is some matrix A times mk, where this A is an n by k matrix. All right. So this is what is called a linear code. Okay, and it turns out that linear codes are pretty good, but then you can't choose any n by k matrix. You have to carefully design the n by k matrix A. All right, so it's going to be a tall matrix. If you view these vectors as column vectors, then this xn, this is your xn, so it is going to be some tall matrix times your mk. All right, so this is one way to think about the channel encoding process. But in general, you could just do it using, as I mentioned, a lookup table.
Okay, sir.
All right. Okay. So this is how the encoder behaves. So what about the decoder? As I mentioned, the decoder at the received vector could be any vector, right? It doesn't necessarily be, it's not going to be equal to the transmitted vector. But so one way to think about, sort of visualize it to get some intuition is the following. So let us assume that you're dealing with some space. I'm just abstractly representing the input space and the output space, xn and yn, as this rectangular region. Right? So each message needs to be mapped to some particular point, so to some particular code words. Right? Maybe the messages are mapped to these particular points. Okay, maybe this is the all zeros message. This is all zero. Only the last bit is 1, and so on. So you go on, and then you have the all ones message. Right? So you can visualize the code words as some special points in this space. Okay, so each message gets mapped to one of these code words. The yellow points are the code words. The yellow points are the code words. So for example, if you look at this particular example, then the code words are special because each component can be either plus square root of p or minus square root of p. It can't be any arbitrary real number. Right? But then if you look at the received vector can be any real vector. Right? So typically, if you transmit this particular code word point, if this is the transmitted vector over here, then the received vector is going to be corrupted, right? So it can be any real vector, but hopefully the noise doesn't perturb this too much. So this is the transmitted vector, but the received vector is some perturbed version of this. Right? So the noise, in some sense, pushes this to this point. So this is going to be your yn. This is what is received at the receiver. Okay. Now this is the received vector, and the goal of the decoder is going to basically be to map this back to the original message symbol. Right. So one way you could think about this, I mean, again, for visualization, it doesn't work for all possible channels, but one way to think about a decoder is that given the received vector, which is some point in this space, you map it to the closest code word point. So you know that all the yellow points are valid code words. So given any received vector, you just map it to the closest code word point. So for example, if this were the transmitted signal, and somehow, because there was a lot of noise, maybe the received vector is somewhere over here. If this is the received vector, yn, then since this is closer to this, closer to the received vector than this point, it could be decoded erroneously as this particular message instead of this particular message, right? So if you've taken a digital communications course, then you would have studied this, right? So when you're doing constellation diagrams, one way to think about it is that in a constellation diagram, you have these constellation points, but then the received symbol could be anywhere in the complex plane, and basically you need a demodulator or a demapper to sort of get back or to find out which constellation point was actually transmitted, and that is typically done using a minimum distance decoder or a minimum distance demodulator. And the same idea carries forward in this case as well, except that now instead of being in 2 dimensions, instead of being in the complex plane, this is going to be in much higher dimension. This is going to be an n-dimensional space because you're using n channel uses, right? So in a basic digital communications course, each transmitted symbol is sort of going to be in 2D, but now we're going to look at n-dimensional spaces, all right? But the basic ideas, the basic concepts still carry forward for n dimensions as well, although it's harder to picturize. So the best way of visualizing it is using this picture over here. Right? So the decoder is going to be a function which takes as input n symbols, and it is going to output a valid code word. All right, a valid code word or a sequence of k bits, effectively. So one way to do it is to use, as I mentioned, the minimum distance decoder. And what does that do? For every point in space, it tries to find the closest code word. Right? So basically, it partitions the space into these subsets such that if the received vector is in this particular subset, then it gets mapped to this. If the received vector is somewhere over here, then it gets mapped to this code word. If the received vector lies in this subset, then it gets mapped to this, and so on. And that's one way of thinking about the decoder or the decoding process. Right? But it doesn't necessarily have to be this. It could be any general decoder where we permit any function, any complicated function is allowed both for encoding and for decoding. All right. Any questions? Okay. So now let's see. So now that we understand what an encoder and a decoder is, at least at a high level, the question is now what is the best that we can do? Now remember that we are characterizing the performance of any coding scheme using these 2 parameters, the rate and the probability of error. The goal is to keep the rate as high as possible and the probability of error as low as possible. And in particular, we're focused on the case where n is very, very large. Right? So we're allowed a very large number of channel uses, and we want to make sure that the probability of error is as small as possible. So the question is, if I demand that the probability of error should tend to 0 as n tends to infinity, then what is the maximum rate possible? If
Sir,
yes,
can you go to the previous slide?
the previous slide, yes.
Sir, little down.
Okay.
The probability of error.
Yes.
Sir, here in the last line, you have taken summation, the probability of mk bar not equal to mk. So
Correct.
it's like decoder output not equal to encoder input.
Correct.
Given mk equal to small mk is the small mk is what, sir? I got a little.
So the small mk is, so you sum over all possible messages, right? So what is this term over here? This is the probability of error, assuming that one particular message was transmitted. Right? So for example, assuming that k is equal to, let's say, 2, okay, for simplicity. So this would be the probability that mk is not equal to, mk hat is not equal to mk, given that mk is equal to 0, 0 times the probability of that 0, 0 was the actual message, mk equal to 0, 0, plus the probability that mk is not equal to mk hat, given that the actual message is 0, 1, times the probability that the actual message is 0, 1, plus this equal to 1, 0, and so on. Right? So this is the probability of error for a random message. So the average probability of error, assuming that mk, the message, is chosen uniformly at random. The probability that mk is equal to some particular sequence, this is 1 over 2 to the k. Right? So each message is equally likely.
Okay, sir.
Okay, and this, each of these terms is sort of the conditional probability of error, given that that particular message was transmitted. That 0, 1 is the actual message, for example.
Okay, sir.
Okay. Now there are different ways. So for example, I could also demand that a different way to look at the probability of error, or a different kind of probability of error, is the so-called maximum probability of error, which is the maximum over all possible messages, that is in this case 0, 0, 0, 1, 1, 0, or 1, 1, of the probability of a decoding error, given that the actual message is little mk, maybe 0, 0, or 0, 1, 1, 0, or 1, 1. Okay, so these two are different quantities, right? So this is the maximum probability of error, and this is sometimes called the average probability of error. And the results could be potentially be different, but it turns out that it doesn't matter. So you need some way of characterizing the error performance of a particular coding scheme. You can either do it using this, or you can do it using this, or a different way. So it could also be possible that the messages are not equally likely. So in that particular case, this would be weighted by a different probability. Right? So in this case, you want to ensure that all the messages are recovered correctly with a certain guarantee, whereas here you are saying that on average, if the messages are uniformly drawn at random, then I want to make sure that the probability of error is small. So in particular, it could mean that in this case, maybe 1 or 2 messages, maybe the 0, 0 message is not recovered correctly at all, but all of the other messages are recovered correctly. So in that case, the probability of error would be small. Whereas in this case, you want to make sure that every single message, 0, 0, 0, 1, 1, 0, 1, 1, all messages are recovered correctly with a certain guarantee. Okay. Okay. So the question we want to ask is, if we want the probability of error to tend to 0 as n tends to infinity, then what is the maximum of k over n, right? So what does this tend to, right? Or what is the maximum of the asymptotic rate? Right? So what is the maximum rate at which we can transmit, or what is the maximum number of useful bits of information or information bits per channel use that we can transmit, assuming that we want the probability of error to tend to 0 as n tends to infinity. Right? So remember, we want the entire block to be recovered correctly with very high probability. Right? So even one bit cannot be in error. All right. So the question is now, what is the maximum rate of reliable communication? And that answer is given by the so-called channel coding theorem, and it says the following. It says that for any discrete memoryless channel, py given x, it is possible, I'm not saying how we can construct, but in fact there exist encoders and decoders such that the probability of error tends to 0 as n tends to infinity. So this is what we want. As long as the rate is less than this particular quantity. Okay, so if I keep the rate, that is k over n, to be less than this quantity over here, some function of px, py given x, and px. So it's some function of py given x. As long as k over n is less than this function of py given x, then it is possible to construct encoders and decoders for which the probability of error tends to 0. I'm not saying that every encoder and decoder which satisfies k over n less than c is going to give a vanishingly small probability of error. All I'm saying is that it is possible. There is some encoder and decoder, some complicated way of mapping from message bits to code word bits and received sequences to decoded bits, such that we are able to recover the original message with a very tiny probability of error. Okay, and this quantity c, which is a function of py given x, the maximum rate of communication, what I'm calling the maximum rate of communication, this is called the capacity of the channel. Of the channel py given x, and it is a maximum of a certain function. So this function is called the mutual information. And this is the second important quantity that we've seen in this course. So the mutual information denoted I of x semicolon y. So this is the summation over all possible x comma y of the joint probability of x comma y times the log of the ratio of the joint probability to the product of the marginal probabilities, px times py. Okay. So this quantity is called the mutual information, and the maximum of the mutual information over all possible px is called the capacity of the channel. And this statement says that if the rate is less than the capacity, then it is possible to construct encoders and decoders for which the probability of error is vanishing. This is the second part to the channel coding theorem, which says that if we try to communicate at a rate above the capacity, if R is greater than C, then no coding scheme, no matter how you try to construct the encoder and decoder, no matter how much resource you invest into it, it is impossible to achieve a vanishing probability of error. So the probability of error asymptotically will be strictly greater than 0. In fact, it's also possible to show that the asymptotic probability of error is going to be 1. Okay, so this says that something is possible, and so this is the first part. And the second part of the channel coding theorem says that if you try to violate this particular property, if you actually try to communicate more information bits per channel use, then no matter what you do, it is impossible to achieve a vanishing probability of error. Okay, and the exact threshold. So if you plot the rate versus the minimum probability of error for the best code, right? You choose the best possible code for that particular rate and then try to find the minimum which minimizes the probability of error, right? So as long as R is less than C and N is very, very large, the minimum probability of error is going to be very small. All right, it's going to be very close to 0. But then as soon as you hit this boundary, if you try to operate at a rate above the capacity, then the probability of error turns out to be very, very large. Right, and this holds for any discrete memoryless channel. Right? So reliable communication is possible at any rate below the capacity, and reliable communication is impossible at any rate above the capacity. So capacity is a strong threshold. All right, and the capacity itself is given by this maximization problem. It is the maximum over all possible input distributions of the mutual information between X and Y. Okay, any questions here? Okay, so let's try to think about why this is a hard problem. Okay, and let us take a very simple example of the binary symmetric channel. Okay, the BSC with probability P, where you can assume that P is some small number, maybe P is 0.1. Okay, so you transmit bits, okay, and what you receive is going to be another sequence of bits, and each bit gets flipped with probability P. Right? If you transmit a 0, then you receive a 0 with probability 1 minus P, and you receive a 1 with probability P. And if you transmit a 1, then you receive a 1 with probability 1 minus P, and you receive a 0 with probability P. That's the BSC. Now, what is the first thing we can think of? The sort of simplest way of, so if I transmit a single bit, a single information bit, then the probability that, what is the probability that this will be decoded incorrectly? Yes?
P to the power alpha, no?
No, so suppose I transmit xi, okay, I transmit xi, which is, let's say, Bernoulli half. I transmit this across the channel, across the BSC P, and I receive yi, right? So what is the probability of error in this case? So no coding at all, I just transmit it through the BSC without doing any additional pre-processing, post-processing. So what is the probability of error? It is a probability that yi is not equal to xi, right? So what is the probability of error for no coding? Right? If the yi is the output of the BSC, then what is the probability that yi is not equal to xi, or what is the probability of error?
So this is for the repetition code you're asking.
No. As I said, forget about repetition code. Just ignore everything below this. I'm just transmitting a single bit through the channel, right? And I'm observing the output, and my goal is to estimate what the transmitted symbol was, what the transmitted bit was.
P will be the probability of error.
Exactly. So the probability that there's an error is a probability that the bit got flipped. Right? So in this case, it is going to be 0.1. Correct? Now, if I transmit n bits, so suppose I do no coding. Okay? So this is assuming that I transmitted a single bit, right? So again, no coding. I transmit xn, a sequence of n IID bits per node half. Okay, I send without doing anything. I just send the bits one after the other through the BSCP. Okay, and I observe the output of the BSCP. Okay, so I transmit 0101 something, and then at the receiver, each bit gets flipped with a certain probability, 1, 0, something. Right, I receive a particular yn. So what is the probability that xn is not equal to yn? So my estimate, I'll assume that my decoder is basically yn. Okay, I do nothing else. So in this case, what is the probability of error?
1 minus p whole power n.
Correct, very good. So there is an error if even one of the bits gets flipped, right? So this is the probability that any of the bits is flipped, which is 1 minus the probability that no bit is flipped, that is xn equal to yn. So this is 1 minus p raised. Okay, yeah, sorry about that. So the probability of error is 1 minus the probability that none of the bits get flipped. So that is 1 minus p raised to the n. So what happens to this as n tends to infinity?
The error.
So this tends to 1 as n tends to infinity, right? So as n tends to infinity, this quantity tends to 0, but it's 1 minus something which tends to 0, so this tends to 1. So if you transmit as is, then the probability that you make an error tends to 1 as n tends to infinity. Now let us think about a simple repetition code. Okay, so basically what do? I repeat each bit alpha times. Okay, let's say I'm transmitting a single bit. Okay, and I basically repeat each bit alpha number of times. If it is 1, then I send alpha number of ones. Okay, so for example, if alpha is equal to 4, then for every message bit 0, I send 4 zeros. If the message bit is 1, then I send 4 ones. Okay, so that's my encoder. That is how my encoder works. Right? So in this case, what is the rate? What is k over n?
1 by alpha.
Correct. So it is 1 by alpha, right? So in every alpha channel uses, I'm sending one bit of information, right? So as alpha is large, the rate is correspondingly small. Okay. Now, so this is the encoder. Now, how would you decode? What do you think is a good decoder?
Majority.
Correct. So majority, right? So you receive the sequence, let's say y alpha, assume that you're sending a single x, and then you receive y alpha, or let me put it in a slightly different way. You have a single message bit. All right, so you have a single message bit, let's say the ith message bit. Now this is converted to x I of 1. This is just repeated alpha times. Correct? So this is basically mi, alpha times. Right? And then this is sent through the channel. You get yi of 1 up to yi of alpha. And then you receive the sequence, right? So some of these bits could get flipped, some of them are received as it is. So if the number of ones is greater than the number of zeros, then you declare it as a 1. Otherwise, you declare it as a 0. Okay, so for example, if you want to transmit bit 0, so this gets mapped to 0, 0, 0, 0. Let's say 4 zeros. And what you receive is a 0, 1, 0, 0. Then you declare 0. If let's say that you received a 0, 1, 1, 1, then you declare a 1. All right. Now there could also be a border case, that is, you could receive a 0, 1, 1, 0, in which case it doesn't really matter. You either decide that you will declare 0 or you will declare 1. So basically you look at the number of ones in the sequence and the number of zeros. If the number of ones is greater than or equal to alpha by 2, then you output 1, else you output 0. Correct? So that is the decoder. So what is the probability of error of the decoder? Right? So there's an error if the number of bit flips is greater than or equal to alpha by 2, which is what?
P raised to alpha by 2.
Is it just p raised to alpha by 2?
Greater than that.
Yeah, but can you give a better expression? So the number of bits could be alpha by 2, alpha by 2 plus 1. The maximum number of bits could be n bit flips, right? Sorry, not n, alpha bit flips. Correct? So what is the term that is going to come here?
N choose alpha by 2.
Correct. Not n choose alpha by 2, it is n choose j, right? Assuming that there are j bit flips, right? If there are j bit flips, then there are j ways of choosing the locations where the bit gets flipped times the probability that exactly j locations are flipped. The n minus j. All right. So this is the number of ways of choosing j locations, and this is the probability that exactly j locations are flipped, j bits are flipped. Right? So this quantity, I mean, this of course depends on alpha, but then you can show that this tends to 0 as if you let alpha to tend to infinity. So if you want to make the probability of error really small, then you should make alpha really small. That's the only way you can do it. I mean, think about it. I mean, even without doing any sort of calculation, you can see that, well, if you will make an error if at least alpha of the bits are flipped, and that happens with a certain probability. And the only way you can make the probability of error really, really small is by letting alpha to tend to infinity. Right? But then if you let alpha to tend to infinity, what happens to the rate?
Very low.
It tends to 0. Right? So the repetition code is not a good code. So just repeating is can get you a small probability of error, but it's going to also make sure that the rate is very, very small. So it's good in terms of error, but then very bad in terms of rate. So that is why designing a good channel code is not an easy task. So even though this particular result was derived way back in 1948, so this was back in 1948, this result was known, but then a good algorithm to achieve this rate, a scheme which ensured that the probability of error tends to 0, came much, much later. It came back only in the early 90s. Right? And this is one of the strong reasons which sort of brought about cellular communications. So designing good codes, good channel codes was essential for cellular communication. Without it, we would not have had cellular communications. Because the only way you can have you can only communicate reliably in the presence of a very noisy medium is by designing a good channel code. All right. So although we knew what the best rate of communication was, we didn't have a good way of achieving that best rate of communication. The only thing we knew was how do we do repetition coding, and repetition coding is not good because the rate is very, very small. All right.
So
Yes.
can you go to that formulas for like
This.
no sir, probability of error? Now you took no, so like NJ.
Yes.
So what is it that you've written? Number of
So this is the number of ways of choosing j locations
okay.
out of n, j out of n locations. All right. So the probability that the number of bit flips is greater than or equal to alpha by 2 is the probability that the number of bits is exactly alpha by 2 or exactly alpha by 2 plus 1 or so on. So the probability that the number of bit flips is exactly j, that exactly j bit flips occur, is this probability that number of flips is equal to j. Right? But then it could be any j locations, right? And there are n choose j possible locations. The probability that those j locations are flipped is equal to this.
Okay.
Right? Okay. So we won't explore channel coding in much more detail in this particular course. We have a separate course to deal with that. So from the next class onwards, we'll explore the connections between the entropy, which was sort of the fundamental limit of compression, with the mutual information, this quantity over here, which is basically a fundamental concept which comes in channel coding. And we'll see that these two are related. We'll analyze properties of these as functions of the joint distribution and the marginals, and we'll see some interesting properties. Okay, so the rest of this course will be devoted to studying the properties of entropy and mutual information, and then interpreting those results for concrete problems that we have. Okay, so we'll stop at this point. Are there any questions?
Sir,
Yes.
just one thing, not with respect to what you've taught, just like this information theory, this is a one credit, no, sir. So, how will it be like? You'll conduct an exam, or how is it going to end, sir?
So just one second.